Hi. Okay, now we're continuing on with the second question in our thing. So welcome to AP Chemistry, and let's keep on going. So we have a question from 2003. Question number 5 is about oxalic acid reacting with potassium permanganate. And so in this reaction, a student in a flask dissolves some oxalic acid. So oxalic acid is a solid and it's dissolved in water. And then we take a burette, and I'm going to do that one in purple. So you take the burette and you're going to titrate the potassium permanganate. And so in this problem, we want to know in part 1 what chemical species is being oxidized in the reaction. And so if you look at Leo says Gur, loss of electrons is oxidation, or if you look at oil rig, oxidation is loss. So we're looking at the species which loses electrons. And so if we look up here, we're going to want to look at all of our species up there, all of our compounds, and figure out which one is actually losing electrons. And so if we come up here, and let's go ahead and take a look at a little space there. If we take a look at this first one, we have oxygen. Oxygen, this is not one of our exceptions where it's peroxide or it's with fluorine, so it must be a -2. And so if we have 4 of them, the oxygen is a -8. All of this has to equal 0 because this is a neutral compound. We don't know the manganese. We don't know what that is, so I'm going to leave a little blank there. But I do know the potassium. The potassium is going to be a +1 because it's a group 1 element. And so I have 1 plus, and I'm going to call this x because I don't know what it is, -8 equals 0. And so if I solve for x, which is my manganese, it's going to be 7, +7. So if I have 1 and 7, a +8, oxygen is a total, all 4 of them together make a -8. We have a neutral compound. So manganese in this compound is +7. Now, if I come over to the other side, I'm going to look at the manganese over here. I know sulfate, the sulfate ion, is going to be a -2. So that whole thing is a -2. I have sulfate here and I have sulfate there. Sulfate didn't really change. So I can just keep that all together and say it's a -2. But if I have, this is a -2, it's a neutral compound, the manganese right here must be a +2. And so I have manganese going from a +7 to -2, or sorry, +2. So that is reduced. That is not our oxidation. So let's keep going. Let's find out. So if we look at this one, we have another oxygen. I'm going to clean this up a little bit. If we look at the oxygen, again, oxygen in this one, it's not one of our exceptions where it's peroxide or it's attached to a fluorine, and it's not by itself, so it must be a -2. And if there are 4 of them, we have a total of -8 for that compound that's neutral. Now our hydrogen is going to be +1, and we have 2 of them, so that's a +2. And I don't know what the carbon is, but I know I have 2 of them. So I have 2 carbons. And so if we figure out what the carbon is, based on the other 2 that we know when we have rules about, we will figure out that that one is actually 3. Our carbon has a +3 oxidation number. And over here we have hydrogen +1. We said our sulfate was -2. And so this one didn't change again. This is still -2. So let's go to this next compound, our carbon dioxide. Oxygen is -2 because it's not an exception. And if we have 2 of them, that's a -4. It's a neutral compound, so the carbon must be +4. So if we look at that, carbon is our compound or our element that's being oxidized. So you can either say carbon is oxidized. It goes from a +3 to a +4. In order to get from a +3 to a more positive number, it has to lose that negative charge. It has to lose that electron, that negatively charged electron. Or you can say our H2C2O4, our oxalic acid, is being oxidized when it goes from that to our carbon dioxide. And there were 2 of them and 2 H pluses, and then we also have 2 electrons. And so this is our oxidation half. And so that is 1 point. So you can say either carbon, or you can say the whole oxalic acid reaction. Now in the next part, part B, it says what substance indicates the observable endpoint of the titration. Now this question, actually to answer it, you would either need to do this in the lab, or you would have maybe a little more information. And if I go up to the top, maybe if underneath this reaction we included the colors, like this one is purple, this one is clear or colorless, this one is also colorless, and all of these are also clear. And so it says what substance indicates the observable endpoint of the titration. And what happens is, as the purple potassium permanganate reacts, and as it's added from the burette, and you notice over here I made the little drops purple. As it comes into the solution, it changes from purple. As soon as it hits the solution, it reacts and it goes colorless. And so as the purple permanganate reacts and becomes clear, the endpoint. And what do we mean by the endpoint? That is when we have equal molar reactions reacting. And so it becomes clear. We know we reach the endpoint when KMnO4 is added to the oxalic acid, the oxalic acid in the flask, and purple color remains. And because it's so dilute, dilute, write that over here, dilute, it will look pink, very, very faint. And so you will see that perhaps later in the year. And so it says, what data must be collected in the titration in order to determine the molar concentration of the unknown permanganate solution? So if we want to know, like our end goal from this titration was to figure out what is the molarity of the KMNO4 and the burette. So the things we would need to know, if we look at this reaction, we want to know the molarity of this one. It's reacting with the oxalic acid. And so the things we would want to know, if we knew the mass of the oxalic acid, we could figure out the moles of oxalic acid. So we need, first thing we would want is the mass. Now, if we knew the moles of oxalic acid, then we could figure out how many moles, using the mole-to-mole ratio, how many moles of KMNO4. And if we knew how many moles of KMNO4 to find the molarity, all we would need is to know how many milliliters of potassium permanganate were added. So maybe you want to know the beginning amount of solution you have in your burette and the final amount. And so those two things, the mass and the change in volume, and I'm going to put change in milliliters or volume. Those two things would allow us to calculate the molarity, because molarity, you need to know the number of moles, and we could get that working backwards by knowing the mass of the oxalic acid, and we need to know how many liters. And so to get that, we would get that from the burette. So those two things are the things we would need to know. And so that kind of answers part of the next question. So if you determine the mass, if you want to know without doing calculations, in other words, explain it, explain how to determine the molarity of the solution. And so if we go back to the data we collected, the mass and the number of milliliters, we're going to use that to figure out the molarity. So step one, find the moles of the oxalic acid from the grams using the molar mass. The next step in that is, if you want to go from one thing to another, if you use the mole to mole ratio to determine how many moles potassium permanganate react. In other words, if you have this problem, and let me give myself a little more space here. Let's see. Okay, a little more space there. So if we know moles of oxalic acid, H2C2O4. If we look up at that balanced chemical equation, we can see that they're in a 5-to-2 ratio. And so for every 5 moles of, let me write the chemical formula. By every 5 moles of the oxalic acid, 2 moles of the potassium permanganate react. Now, the last step is for taking the amount of moles and divide it. So divide the moles potassium permanganate by the volume in liters that you used. And you want the amount that you had to reach the end point. And at the end point, all of this reacted with potassium permanganate. And when you start getting that pink color, that means you're starting to have excess potassium permanganate. And so you don't want the point where this is in excess and your solution in here is turning purple. You want it when it's clear and just starting to turn pink. That means that you have these 2 guys completely used up. And you can figure out how many moles of this you had based on the mass of the oxalic acid. Okay, and going back to part, I didn't go over the points. Part A was only worth 1 point for saying which species oxidized. Part B was worth 2 points. 1 for identifying the species that's reacting, and then another point for indicating that it remains colorless at the end point. Now part C is worth 2 points, as you would expect. 1 point for the mass and 1 point for either saying the change in milliliters or measuring the beginning, the initial and the final number of milliliters in the potassium permanganate burette. And then part D. Part D is worth 3 points. 1 point for each of these labeled steps. Finding the number of moles from the grams, using the mole-to-mole ratio to determine how many moles of potassium permanganate from the oxalic acid, and then the last step to find the molarity by dividing the number of moles you determined in the previous step by the volume in liters to reach that end point. And so the last point is kind of our error analysis question. And so if we look at that, how would you calculate the concentration of potassium permanganate if you added 40 milliliters of water initially instead of 30? Now, if we go back to the steps that we looked at, we put a solid oxalic acid in the beaker and then added in 30 milliliters to dissolve it. And then we did that reaction where we added in the potassium permanganate to the end point. And so looking at these steps, if you had 40 milliliters, the oxalic acid would be more dilute, but that doesn't matter. Nothing would really happen. So there would be no effect on the calculated concentration. And why would there be no effect on the calculated concentration? Because the grams of oxalic acid are the only thing that affects that calculation. And so if we don't change the mass of oxalic acid that we added, we don't really care how much water was added to dissolve. So an extra 10 milliliters doesn't change the mass. So in other words, the grams of oxalic acid is used to calculate the moles of oxalic acid, and therefore also the moles of potassium permanganate. The water used to dissolve it has no effect. So the same amount, more or less, doesn't matter. What matters is how much oxalic acid was added. Okay, on to the next question. Question number 3 in our packet is from the year 2006. So hopefully you kind of answered these questions and you're following along, checking your work, and you try to work them before I do. So we are going to use chemical and physical principles to account for each of the following. And so in this, number 1 asks, an aluminum container filled with an aqueous solution of copper sulfate eventually developed a leak. Answer the question, but it says include a chemical equation with your answer. Now, if it says include a chemical equation, include it. In fact, in this one, it's worth the first point. So what's going on if you have an aluminum container and you react it with copper sulfate and it develops a leak? And so hopefully you've recognized that your aluminum is actually reacting with the sulfate. And so you have a single replacement reaction in which positive ions are switching places. And so now you have aluminum sulfate. And so here we have a 2 and here we have a 3 when you balance charges. And we have copper. Now, on the AP test, whenever you are giving a chemical reaction or a chemical equation, you are supposed to do that in net ionic form. And so if we write the net ionic equation of this reaction, we have aluminum, the element, reacts with copper. And because this is given to us, it must be a +2 ion. And it is forming aluminum. That would be a +3 and copper. Now, I didn't balance it in that first equation, but I'm going to go ahead and do that in the second one. And if we look at the second one, if we're going from aluminum to this one, we have a change of 3 electrons. In this one, we have a change of 2 electrons. In fact, actually looking at the rubric, you do not need to balance it. If we did balance it in the top one, we would have a 2 here, right there. And what, a 3 here and a 3 here. And I think we're good. But in the bottom one, we can leave it like that. We would have to balance it if they ask for maybe more. But the next step would just be to talk about why. And so if we look at that, if you look at the activity series, if we look at that activity series, the activity series indicates that aluminum is more active than copper. And so okay, now second question, there were two points in that last question, one for the reaction and right here, and one for the explanation. Let's go to part B. It says the redness and itching of the skin caused by ant bites. And when an ant bites you, they inject methanoic acid into you. But that can be relieved by applying a paste made from water and baking soda. And so it says include a chemical equation with your answer. So they give us a chemical formula for methanoic acid. And interesting little side note, methanoic acid was first discovered by crushing the bodies of dead ants. Kind of gruesome, but this is used in a lot of industrial applications now. But our methanoic acid will react with baking soda, and baking soda is sodium bicarbonate. And so there is our first half of our reaction. And when these two guys react, this is an acid. In this case, the sodium bicarbonate or sodium hydrogen carbonate will act as a base. And you will have sodium reacting with this methanoic acid. And what's the difference? How do you know it's an acid? It loses a hydrogen, and you form the other product. Now, the other product is the base, and the base is going to accept a hydrogen, and so you have this compound. But this is carbonic acid, and we know carbonic acid breaks down. And so what you really have going on here is you have your methanoic acid. When it reacts with that sodium bicarbonate, you get this sodium bicarbonate, or sorry, sodium carbonate. I put on an, let's see, sodium methanoate. And then the other product, this decomposes to H2O and CO2. Okay. So why does that happen? The baking soda undergoes, since it's an acid and a base reacting, it's called a neutralization reaction. So it undergoes a neutralization reaction with the 2, 1, with the methanoic acid, our HCO2H. So when that happens, the redness subsides and the ant bite pain is relieved. And so part B is also worth 2 points, 1 point for this equation and 1 point for saying it undergoes a neutralization reaction. You have an acid-base neutralization there. Okay, and now for the last question. The last question I'm going to do on the next video. So go ahead and start working that while you pull up the next video.